Okay, so, somewhere out there, right now, space itself is humming. Not a metaphor. Scientists have actually detected a low, constant vibration running through the universe, a background noise made of gravitational waves. And for years, nobody could fully explain where all of it was coming from. But a new study just did something wild. It traced part of that hum back to objects that technically shouldn't exist anymore. Stars made almost entirely of dark matter, that died over 13 billion years ago. Yeah. Let that sit for a second. We're talking about dark stars, giant, invisible fuel stars from the very edge of cosmic time, and the idea is that their deaths might still be echoing through the universe today, in the form of gravitational waves we can actually measure. So today, let's get into how scientists think dead stars from the dawn of the universe are still whispering to us, right now, through spacetime itself. Let's start with the mystery that kicked all of this off. Back in 2023, an international group of researchers confirmed something huge, a constant background of gravitational waves, picked up using something called a pulsar timing array. Basically, pulsars are dead stars, spinning insanely fast, and blasting out beams of radiation like cosmic lighthouses. Those beams hit Earth on a super precise schedule. So precise, that if a gravitational wave passes through, it stretches and squeezes space just enough to throw off the timing, by fractions of a second. Now imagine doing that across dozens of pulsars, for years. That's basically a galaxy-sized gravitational wave detector. And when scientists did that, they found this constant, low-frequency hum sitting in the background of the universe. The leading explanation: supermassive black holes, some over 1 billion times the mass of our Sun, slowly spiraling together before merging. Makes sense on paper. But here's where it gets messy. The James Webb Space Telescope keeps spotting supermassive black holes that are already huge, in a universe that's less than 1 billion years old. And the problem is, the usual black hole growth process, feeding, merging, growing bigger, should take longer than that. Way longer. So how are these things already massive, this early? Let's slow down on that for a second, because it's a genuinely weird puzzle. Building a supermassive black hole the normal way is a slow grind. A regular star collapses, forms a black hole maybe a few dozen times the mass of the Sun, and then that black hole has to feed, merge with other black holes, feed some more, merge again, over and over, for a very long time, before it becomes supermassive. That process alone is estimated to take well over 1 billion years to get anywhere close to the masses we're talking about. But JWST keeps finding black holes that are already there, fully formed, sitting inside galaxies that existed less than 1 billion years after the Big Bang. It's like finding a fully grown oak tree in a forest that was planted last week. Something doesn't add up, and astronomers have been arguing about this exact contradiction for a while now. That question is exactly where this new research steps in. Two scientists, Sohan Godla and Cosmini Lee from Colgate University, asked a pretty bold question: what if the seeds of these black holes weren't small at all? What if they started out already massive, because of something called a dark star? Here's the concept, and stick with me because it's genuinely strange. A dark star isn't powered by nuclear fusion, like our Sun. Instead, it's powered by dark matter particles annihilating each other inside its core. Because of that, it stays relatively cool. And because it stays cool, it doesn't blow itself apart the way normal stars eventually do. It just keeps pulling in more and more matter. Over time, that adds up. These things could have grown to millions of times the mass of the Sun, while a normal star tops out way, way below that. Think about the difference between a candle and a wildfire. That's roughly the scale gap we're talking about here, except this candle just kept growing, quietly, in the dark, for millions of years. Eventually though, physics catches up. Even a dark star can't hold itself together forever once it gets that massive. So it collapses under its own gravity. And when it collapsed, it didn't fade away quietly. It left behind an enormous black hole seed, one that starts its life already thousands, maybe millions, of times heavier than the seeds normal stars produce. Seeds heavy enough to explain why supermassive black holes were already showing up so early in the universe's history, without needing a billion years of slow feeding to get there. So that's the origin story. Now here's the part that connects it to today. Godla and Elie modeled how these black hole seeds would behave over billions of years, how they'd merge, how often, and under what conditions. And what they found is, if enough of these dark star remnants existed in the early universe, their long chain of mergers could actually be a major contributor, maybe even the dominant contributor, to that gravitational wave background pulsar timing arrays picked up back in 2023. In other words, the hum we're detecting today might not just be recent black holes merging. Part of it could be an echo, a leftover signature, from stars that died before galaxies even had their current shapes. And here's what makes this so satisfying from a scientific angle: this isn't just a story, it's testable. The researchers didn't stop at, wouldn't it be cool if? They actually built a model, tracking how these black hole seeds would have formed, where they would have lived, inside massive clumps of dark matter called halos, and how often they'd realistically collide over billions of years of cosmic history. Then they compared what that model predicts against the actual gravitational wave background we've already measured. That's the difference between speculation and science. You take a wild idea, and you force it to make a prediction that reality can either agree with, or shut down completely. That's the loop I promised you at the start, by the way. Stick around, because there's a twist coming. This signal might actually work like a cosmic thermostat. Here's why that matters. Godla put it in a pretty clever way: if there were too many of these massive dark star remnants early on, the gravitational wave signal we detect today would be way stronger than what we actually observe. But if there were too few, something else would have to explain how supermassive black holes grew so fast. So the exact strength of this background hum becomes a kind of dial, one that tells scientists roughly how common these heavy black hole seeds were, 13 billion years ago. Basically, pulsar timing arrays weren't just listening to recent black hole mergers. They were listening to fossil evidence, buried inside a signal that's been traveling toward us since almost the beginning of time. And that's honestly the coolest part of this whole study, right? We're not talking about new telescopes seeing further. We're talking about researchers reading information that was already sitting in data we collected years ago. We just didn't know what to look for. Think about what that actually means for a second. Every pulsar in that array has been ticking away, faithfully, for years, sending out its beam like clockwork. Nobody built those pulsars to study dark stars. Nobody designed the timing array with ancient dead stars in mind. And yet, buried inside those tiny timing delays, milliseconds off schedule, spread across a whole network of neutron stars, might be a signature from an era so old, galaxies hadn't even finished forming their basic structure. That's kind of the beauty of gravitational waves as a tool: they don't fade the way light does. Light from the early universe gets stretched, redshifted, sometimes absorbed entirely by gas and dust in between. But gravitational waves mostly just pass through everything. Space itself carries them, almost untouched, across billions of years. Which means if this signal really is there, it's one of the most direct messages we could possibly receive from an era we can barely observe any other way. So here's a question for you: if gravitational waves can carry fossil signals from the first billion years of the universe, what else might already be hiding in that background hum, that we just haven't figured out how to decode yet? Now, is this confirmed? Not yet. Dark stars are still a theoretical model, nobody has directly observed one. But that's actually what makes this research interesting. Instead of trying to spot a dark star directly, which might be nearly impossible, the researchers found an indirect way to test whether they existed at all, through their gravitational aftermath, billions of years later. Elie described it as a completely different way of testing an old idea, one that doesn't need us to see a dark star with a telescope, just to notice its fingerprints in spacetime. And that reframing matters more than it might sound like at first. For years, the plan for confirming dark stars was, find one directly, maybe as a strange, unusually bright object from the early universe, using something like JWST. But direct detection like that is incredibly hard. These objects are ancient, distant, and might look confusingly similar to very early galaxies or unusual stars. This new approach basically sidesteps that whole problem. Instead of hunting for a needle in a haystack 13 billion light-years away, you listen for the vibration the needle left behind, long after it disappeared. It's a bit like trying to prove a firework went off, decades after the fact, not by finding a photo of it, but by measuring the very faint rumble still traveling through the ground. If you're enjoying this kind of deep space rabbit hole, drop a like. It genuinely helps this channel keep making videos like this one. Where does this go next? Better pulsar timing measurements, and a clearer picture of early black hole populations, could either strengthen this theory, or rule it out. Existing arrays are already gathering more years of data, and every extra year sharpens the picture of that background hum, refining exactly how strong it is, and how it's distributed. Combine that with more early universe black hole discoveries from JWST, and researchers should eventually get enough evidence to say, with real confidence, whether dark stars were the missing piece, or just an elegant idea that didn't survive contact with better data. Either way, that background hum in the universe just became a lot more interesting than, probably just black holes merging. Because if this holds up, it means part of the vibration running through space right now isn't from something happening recently. It's an echo from stars that burned dark, grew massive, collapsed, and vanished, before the universe even had its first billion years behind it. Stars nobody ever saw, made of something nobody has ever directly touched, still leaving a mark on the universe, long after they stopped existing. And somehow, that whisper is still reaching us. If this blew your mind a little, subscribe, there's a lot more of this universe left to explain. See you in the next one.